Hey everybody, so as promised, I want to make a little mini lecture on confounding that will hopefully help you in your understanding of the concept of confounding and will help you as you're studying for the quiz this week as well as our exam this next week and the final as well. So we remember that confounding is a bias. At the end of the day, it is a bias because it is something that could potentially lead us to getting some misleading results. And so it's a bias that's caused by mixing the effect of the exposure of primary interest with extraneous risk factors. So as we've been studying the associations between exposures and diseases, confounding variables are these variables that can come into play and mix with our exposure of interest and could actually explain the associations that we find. So, for instance, have this example of if smokers have other exposures that are different than non-smokers, and maybe those are the real culprits of cancer. And so this is something that tobacco companies and some politicians have posited that maybe it's not smoking that's actually associated with cancer. Maybe it's just all the things that is associated with smoking that actually could cause the cancer. So the things as far as where people live, so air pollution and all these things that may be mixed with this exposure that could be actually causing the risk. And so I gave a couple of examples in class, and so this was one that I wanted to just show that confounding in kind of the broad abstract sense can be kind of complicated, but it really makes a lot of intuitive sense when we try to think about it. And so this is one of the examples that I had that we find that birth order is associated with Down syndrome, and that is saying that the higher in the birth order, the more likely that child is to have Down syndrome. So if they're the third or fourth child in the family, they're more likely to have Down syndrome. And now this is a true association. We actually do find this, but it's not being explained by birth order. And so that's what we're trying to test when we're looking at confounding is can this association that we find be explained by some other variable? And so for instance, in this case, we do find that it is explained by another variable. It's explained by mother's age. So we know that older women are more at risk for having a child with Down syndrome. At the same time, older women are more likely to be having their third and fourth child. And so that is how we would explain away this association. We'd say that birth order does not actually have any kind of risk with Down syndrome. The risk is all attributed to mother's age, and mother's age just happened to be associated with birth order. And so we went through this in class, and you can maybe think of a few examples now as you're listening to this of what maybe are some confounders for physical activity and cardiovascular disease. So we do know from research that physical activity is associated with cardiovascular disease, and so that it would be a risk factor. But what are some potential things that may be associated with physical activity and may be causing an increased risk at cardiovascular disease that maybe could explain away this association? So there's been quite a few things that have been put forward, such as diet. So those with a poorer diet exercise less, and so maybe it's this poor diet that's actually causing cardiovascular disease more so than the physical activity. You think of maybe where people live or jobs people have. So people that are maybe working more jobs, they're working two jobs and they can't have as much exercise, and so maybe it's this they're working multiple jobs and maybe the stress from that is actually leading to cardiovascular disease rather than physical activity. So a confounding variable would be something that would explain away this association between physical activity and cardiovascular disease. So there are going to be things that are associated with physical activity and associated with cardiovascular disease, like diet. But if we still see that physical activity is a risk factor for cardiovascular disease, these variables aren't going to be confounders. They're just going to be other risk factors for cardiovascular disease that also just happen to be associated with physical activity. And so this is our broad model that we have. So this link between exposure and disease, we see the exposure pointing towards disease. And so we have a causal model, we're saying that the exposure leads to disease. And then we have the potential confounder. So the potential confounder is also leading to disease and is maybe also associated with this exposure. You see that double-sided arrow, meaning that there's an association between these two factors, but one isn't causing the other. They just happen to be grouped together. So this is our conceptual model, and this is maybe what it looks like with some examples. So smoking leads to lung cancer, but we have this confounding variable that's factory work. So factory work could also lead to lung cancer. Maybe factory work is also associated with smoking. So those that work in a factory are more likely to smoke. And so maybe this association that we see between smoking and lung cancer could actually be contributed to factory work. And so this is how we would recognize confounding. So it must be an independent risk factor for the disease of interest. And so we've said what that means is that our confounding variable has to be a risk factor for the disease of interest independent from anything else. That means that when you control for all other potential variables, that this confounding variable is still putting people at risk for disease. And the confounder must be associated with the primary exposure of interest but not be a result of the exposure. So there can't be a causal pathway where this exposure is actually causing the confounder, but we just happen to see an association. So like between smoking and factory work. So people that work in a factory smoke more. There's not a causal relationship there. It's just those two things just happen to be associated with each other. And so here's an example that we went through in class, that maybe air pollution is causing bronchitis. So we know that people that live in an area that have higher air pollution, there are higher rates of bronchitis. But maybe this relationship could be explained by smoking, to where the apparent effect of air pollution on bronchitis may actually be due only to smoking. And so this is only going to occur if we find that smoking is a risk factor for bronchitis and smoking is associated with air pollution. And so our first criteria said cigarette smoking is a risk factor for bronchitis. And the second criterion, it's associated with air pollution. So those that live in a high air pollution area are more likely to smoke. We can even say those that are more likely to smoke are more likely to live in an area that has higher air pollution. And so we're concerned about the potential effects of confounding through any epidemiologic study that we're going to conduct. So we're particularly concerned when there may be multiple causal pathways to a disease. And so we can think about that with a lot of the chronic disease, leading causes of death, such as cardiovascular disease, cancer, diabetes. We know that there's lots of different risk factors for these diseases. And if we're trying to establish which ones are actually causing the disease, we have to control for all these different risk factors that may be associated with each other, such as diet, exercise, smoking, income, place of residence, stress, all these kinds of things that are really associated with each other. A lot of times those that are at risk for one of those exposures are at risk for those other exposures too. And so we're trying to find which ones are causing the most risk for the disease we're interested in. And so when we want to evaluate whether a particular relationship between an exposure and disease is causal or it could be due to another risk factor. So remember our first objective in epidemiology. We want to establish that there is a causal link between an exposure and disease. Not just an association, but we could say that this exposure is actually causing disease. When we think about in public health and as health educators, that's really what we want to do, is how can we reduce the risk of exposure or just reduce the amounts that people are exposed to these exposures, so such as smoking or physical activity, lack of physical activity. And we want to establish if these are actually causal relationships, then we can establish programs and policies that can try and reduce the rates of exposures that will in time reduce rates of disease. And so it's really important for public health that we can establish those relationships, a causal relationship. Because if we're just going after or developing programs or policies that try to reduce an exposure that's actually being confounded by another variable, we're going to end up wasting our resources and wasting time, and rates of disease may not be decreasing at the kind of rates that we'd like to. So confounding has a really important impact on public health. So it's important to remember that all study designs and any exposure disease association that we are interested in looking at is going to have some kind of risk for confounding. And so how do we determine if a variable is in fact a confounder? And so I've put in that this first method that we look at, as I've said a few times now, determine whether this confounding exposure is an independent risk factor for disease, and if it's differentially distributed between exposed and non-exposed. And so that gets a little wordy, but really all that's saying is, do we see that this confounding variable is at higher rates in the exposure group than it is in the non-exposure group? And so a couple ways that we do this is to determine if it's an independent risk factor. We can get the relative risk for the confounder in the non-exposed group. And so what that does is we actually control for the exposure, and then we can get the rates of disease that can be contributed to the confounder independently. So for instance, what's the relative risk of bronchitis for smokers versus non-smokers for everyone living in a low pollution area? And so we're trying to test if this relationship between smoking and bronchitis is actually an independent risk factor. So to do that, we would have to control for the potential effects of air pollution. So by just looking at those that are in the low air pollution area, we can get the risk for bronchitis for smoking. And to also test if this confounder is associated with the exposure, which is number 2, then we can compare the proportions of the confounder between exposed and non-exposed groups. So for instance, those that live in high air pollution areas, are they more likely to smoke? So thinking about comparing these proportions, we can think about it as we're comparing the prevalence of the confounder in the exposed group and the prevalence of the confounder in the non-exposed group, and compare those proportions. So here's my data setup of air pollution and bronchitis. And so I can compare or calculate a relative risk for bronchitis for those that live in a high air pollution area compared to those that live in a low air pollution area. And so I would encourage you right now to pause the video and just calculate that relative risk. And as you're doing that, as we're thinking about relative risk, I think it's going to be good for you to break it down into parts. So the first part would be, what's the incidence of bronchitis for those that live in a high air pollution area? And so when you get that, you can compare that then, without calculating the relative risk, to the incidence of bronchitis in the low air pollution group. And so before you even calculate relative risk, you should see that, okay, these incidence rates are different. The incidence rate for bronchitis for those that live in a high air pollution area is going to be higher than the incidence rate for those that live in the low air pollution area. And so just by comparing those rates, just by eyeballing them, you're going to be able to see that those that live in a high air pollution area have higher rates of bronchitis. So go ahead and pause the video, calculate the relative risk, and see what you get. And so hopefully you were able to get the relative risk of 2.3. And so just looking at these incidence rates, you can see that in the higher pollution area, 0.136, we could calculate that out to a percentage or to a per 1,000 rate. So let's just think about percentages. So 13.6% of those that live in a higher pollution area have bronchitis, as compared to those that live in the low air pollution area is going to be 5.9%. So before we even calculate the relative risk, we can see that those that live in a high air pollution area have higher rates of bronchitis than those that live in a low air pollution area. So there's relative risk of 2.3. Those that live in a high air pollution area are 2.3 times more likely to have bronchitis than those that live in a low air pollution area. And so this is a real association that we see. But what we're doing with confounding analysis is trying to see if this association that we see, and we see there's an association by this relative risk of 2.3 being greater than 1, this association that we see can actually be explained by another variable. And so potential confounding variable is smoking. And so is this association being confounded? And so to evaluate this, we would have to see if smoking is an independent risk factor for bronchitis and smoking is associated with air pollution, and looking for those different distributions between the exposed and non-exposed groups. So it's really important in our planning stages too that when we're setting up a study, we're thinking about these potential confounders. So for instance, that's the whole reason that we do matching in a case control study, is we're trying to control for potential confounding variables. So if we think of something like drinking and liver disease. So if we don't match on sex in this case, then we might get different results. We know that men are more at risk for liver disease, and they're also more at risk for risky drinking behavior. So they're going to drink more, they're going to binge drink more. And so if we want to test what the relationship is between alcohol and liver disease, then we have to control for the gender. Because if we don't control for that gender, then we're going to get very different results. And if we are able to control for that by matching, then we're going to get just the results that we can attribute to alcohol. So I hope that made sense. And so one solution that we can have as we're in this planning stage is stratification. So I want to bring up this example to make a point. So we've seen from research that diet and exercise are both risk factors for cardiovascular disease. But we also know that diet and exercise are associated. So those that have a poorer diet, calorie-rich diet, are also more likely to not engage in as much physical activity. And so we've seen that poor diet and lack of physical activity are both associated with cardiovascular disease. But since they're both associated with each other and they're both potential risk factors for cardiovascular disease, we don't know which one is actually causing cardiovascular disease. So this is an important point. It could be one that's actually the causal factor. It could be both. So this is what we test for with confounding analysis. Now, if we find that independently they are both associated with cardiovascular disease, then there's not a confounding problem there. Even though they're both associated and they're both risk factors for the disease, that is diet and exercise, are both risk factors for cardiovascular disease, and they're both associated with each other, they would not be confounding each other because they are both independently risk factors for cardiovascular disease. If you have questions on that, I can explain that a little bit further, either in class on Tuesday or send me some emails, and I can kind of try to clear that up a little bit because I think that's a really important point as we think about confounding. And so the process of stratification is just breaking our data down into groups or strata, and we can base those groups down to in any fashion that we like, but potentially in confounding, we want to break those down on the confounding variable. And so if we put the groups into groups based on that confounding variable, then we want to see if that relationship between exposure and disease is actually due to exposure. And if it is, then we would expect to see an association between the exposure and disease in both of the groups. And so this would be what a stratified data would look like for air pollution and bronchitis that we've been looking at. And so everyone in the left table is a smoker. Everyone in the right table is a non-smoker. And so by doing this, we've controlled for the effects of smoking. So for instance, in this right-hand table of non-smoking, we can compare, or we can look now at the association between air pollution and bronchitis that actually controls for smoking. It controls for smoking because everyone in this right-hand table is a non-smoker. So we know we have no effects of smoking that are creeping into our results here in either of these tables. So to evaluate confounding, first, is smoking an independent risk factor for bronchitis? And so the way we do that is we would compare the bronchitis risk between smokers and non-smokers in our non-exposed group, in the low air pollution group. And so calculating out a relative risk for that, and I went ahead and just put the table down here. I set a 2x2 table up. You could do that from the two tables that are here. So looking at that low air pollution group in both the smoking and non-smoking groups, we can actually get the relative risk of smoking to bronchitis. And so you can pause the video and try to calculate the relative risk now, but you're going to get a relative risk of 4.04. And now we want to see if smoking is associated with air pollution. And so the PowerPoint that I showed last week looks a little bit different than what I'm showing now, but I want to make a point that what we're really testing is just this association between the confounding variable and the exposure. So if we compare these proportions, we want to look at what's the percent of those that live in a higher pollution area in the smoking group. And so if we go back to our tables here and look at how many of these people in the smoking group live in high air pollution area. And so that gives us a rate of 83.2%, which means that 83.2% of the smokers in our data live in the high air pollution area. And then calculating out that rate for the low air pollution area as well, we see it's 18.6%. So we see that there is an association between smoking and air pollution, and that's because we have very different rates of air pollution in our smoking and our non-smoking groups. And so now we get into calculating relative risk for the effects of air pollution separately for smokers and non-smokers. So if air pollution is actually having an effect on bronchitis, then we would expect to see an association between air pollution and bronchitis for smokers and an association between air pollution and bronchitis for non-smokers. So pause the video, take some time to calculate these relative risks, and see what you get. So hopefully you were able to find that the relative risk among smokers is 0.99. And so we had a little conversation about this in class of, this was essentially 1. So let's break this down a little bit further too. If you calculate your relative risk, you're getting the incidence rates for high air pollution and the incidence rate for low air pollution. So if you take it a step back and just compare those incidence rates, I think that the incidence of high air pollution in the smokers group was about a little over 16%, and the incidence in the low air pollution group was a little over 16% as well. So even just comparing those incidence rates, you're going to see that there's not much difference in the high air pollution group and the low air pollution group. And so while 0.99, yes, is less than 1, I really want you to be able to see that the strength of this association is very, very, very weak. And that's because the incidence rates are almost the same. And it's the same thing for non-smokers. It's 0.97. Again, less than 1, but comparing those actual incidence rates, you're going to see there's not much difference between those incidence rates at all. And so if we remember that the relative risk among our total population was 2.3, we see that these rates are very different in the stratums than they are in the total population. So if air pollution was actually having an effect on bronchitis, was actually putting people at risk for bronchitis, then we would expect to see a similar relative risk to this 2.3 in the smoking group and in the non-smoking group. But since these relative risks are much lower, these associations are much lower, and have essentially gone to being where there's no association, then we'd say that smoking is really confounding this relationship. So from this example, we see that smoking is a confounder of this association between air pollution and bronchitis. And part of that is that smoking is a risk factor for bronchitis, and we know that from calculating out the relative risk. We controlled for air pollution to a relative risk of 4, meaning that those that smoke are 4 times more likely to have bronchitis than those that do not smoke. And we know that smoking is also associated with air pollution. And so these percentages are different than what we saw in the few problems above, and that's because we actually looked at the proportions of smokers in each of these areas. So, you can really look at the proportions either way. The proportion of the confounder in the exposed and non-exposed group, or look at the proportions of the exposure in the confounding group and the non-confounding group. So either way, you're going to get that there's an association between the two. And so finally, we want to test to see if the association that we found is actually strong enough to be able to determine that there's confounding relationships. So there may be times where you find that an association, let's just go back a couple slides, you may find that this association may be reduced, but we may see that there's still an association. Now in this case, we found that there was no association between air pollution and bronchitis, or this very, very, very weak association, 0.99, 0.97. But there may be times where we still see associations between the exposure and disease. But we want to see if this confounding variable is having enough of an effect on the relationship that we would determine that the association that we saw between the exposure and disease is contributed to the confounder rather than the exposure actually being a risk factor for disease. And so that's what we're doing in this method too, and with our stratum-specific rates. So we know that smoking is a confounder because it meets these two criteria. The stratum-specific rates are either both greater or both less than the crude relative risk, and so we know that they were both less because 0.99 and 0.97 is less than 2.3. And we also want to test if it's large enough. So is this crude relative risk for our association, is it very different, so at least 20%, than our stratum-specific relative risks? And so if it's large enough, so at least 20% different, then we would determine that this relationship is being confounded. And so this is how you would calculate out those to see if it's at least 20% different. Now I'll put in here that you could also use an odds ratio. Each of these examples that we've used has used relative risk, and I think we'll stay consistent with that and just use relative risk throughout the rest of class. But know that we can use an odds ratio as well to test association. So if both of our stratum-specific rates are less than the crude rate, then we would take 20% off of our crude relative risk, subtract it, see if they're still both greater than the stratum-specific rates. They're both greater than the crude rate, which we haven't seen in class, but if we did that, then we would take our crude relative risk and we would actually add that 20% and see if they're still less than both the stratum-specific rates. And so we know from our example that yes, they are 0.99 and 0.97 were both less than 2.3. And we also know that there's at least 20% different between the crude relative risk and our stratum-specific relative risk. And so that relative risk of 2.3, if we take 20% off of that, then we're left with 1.84. And so since 1.84 is still greater than 0.99 and 0.97, we would determine that yes, smoking is a confounder for the relationship between air pollution and bronchitis. So I hope this was helpful. I was going through a big example again that we did go through in class, but for confounding, I want you to remember that it is something that it is intuitive. So, but is very important for how we understand public health. And so these are the things that I want you to consider when, as you go through the program and as you get into the workforce and you're either developing programs or helping to work on different public health programs or public health policies, and you may be trying to address certain exposure and disease relationships. It's really important to be thinking about what are the other potential factors or potential associations that may be affecting how we understand the relationships between exposures and diseases, because that's going to be really important for when you're establishing um, different public health programs. So I hope this was helpful, and if you have any more questions, then please take some time to meet with your classmates, email me kind of office hours, and we'll try to get you where you need to be.